So, from this class we will be starting our discussion on the backend design of VLSI systems. In the ASIC design flow, if you recall, we had mentioned earlier that there are a number of different steps we have to go through. Some of them we can categorize as the front end design, some of them we can categorize as the back end design. Just to recall, we would very fast go through the different steps, and we will also have a very quick review of the VLSI design styles in order that you can appreciate or understand some of the algorithms that we will be discussing subsequently under this. Okay. So, our broad topic of discussion today is some basic concepts in VLSI physical design automation. Fine. So, we start by again looking at the VLSI design cycle. Now, just to recall, in a typical VLSI design today we have a very large number of devices, and obviously to obtain reasonable amount of performance we need optimization at every phases of the design. Moreover, we need to do it fast because there is competition from vendors, there is a time to market, some kind of a constraint, and cost of design is of course an issue. See, earlier starting from a system specification we could also carry out a manual or a semi automated process in order to arrive at the chip, but today with the kind of chip sizes we talk about, complete automation tools are mandatory. So, just we have to rely very heavily on automation tools in order to start from the system specification down to the chip level. Now, in the VLSI design cycle, I had already mentioned earlier at the very beginning that there are a number of different steps we need to go through, starting from the system specification, functional design, logic design, circuit design. They fall under the purview of synthesis. Then you will have to carry out physical design to arrive at the layout possibly, if the target is an ASIC, design verification, fabrication, and finally packaging and testing. So, there are a number of steps in the VLSI design cycle. So, now we will be concentrating on physical design, which follows this step of synthesis. After synthesis is complete and we have obtained a circuit description possibly in the form of a netlist. So, starting from there we will have to move through several steps in order to get a much lower level description of the design, which I had said, if our target is an application specific IC, that can be a layout. Okay. So, these are the different steps which have to be gone through, and we are mostly interested right now in this step of physical design. So, broadly in the physical design phase, we have a circuit description as the input. This can be a netlist, and from there we typically go towards a layout description, and this step of transformation is typically carried out through an intermediate description which is geometric in nature. Geometric in nature, why? Because now we think about the silicon floor, we think about the blocks or the components we need to put in the silicon floor. We need to think about the exact geometry of the interconnecting paths and so on. So, at this level we talk about rectangles and straight lines, right. So, ultimately our objective is to put them on the available area in a suitable way, so as to optimize the performance based on several criteria will be seen. Now, the different steps or the main step, these are the basic steps involved in this process are, of course, if it is a big design you have to do some partitioning, floor planning and placement. Just like when you are building a house, you have to make a plan at the beginning. First you plan roughly where you will put what, then you refine your specification with respect to the netlist, and you can carry out the actual placement. then you have to interconnect them, routing, and finally you will find that after everything is over, still you can do some kind of compaction to reduce the total area. So, this compaction is a post processing step, you can say. So, after everything is done, you typically do compaction. Now, I am yes.
So you mentioned routing after floor planning.
Routing after floor planning, yes.
How will you decide how much space you should leave between the two?
Okay, we will see later that means when you are doing floor planning or placement, we have to have a very rough or gross estimate regarding the area we have to leave aside for interconnection, but that is an estimate. Unless we carry out the actual interconnection, we cannot know the exact amount of space that will actually be required.
There might be an iterative loop then?
Yes?
There might be an iterative loop between floor planning and routing then?
No, there is no iterative loop as such, because floor planning and placement are some kind of a rough placement. After routing, the geometry will be fixed. Placement says that I have to put this block to the right of this block to the bottom of this block. There will be some space in between for routing. But when this routing step is carried out, you will find out exactly how many tracks of wires you have to leave aside between the two blocks. So, the exact geometry will be finalized only after routing. This floor planning or placement are tentative. Okay. So, after routing it gets finalized. Fine. Okay. So, I am showing you the overall steps once more. So, the first step is design entry. Design entry is typically through a hardware description language, you know. You specify the behavior. Next step is of course synthesis. We have talked about several aspects of synthesis already. This may involve high level synthesis, logic synthesis, everything. So, typically during or after synthesis you go for partitioning. So, usually we partition either the CDFG or the netlist, depending on how we are using it. So, after floor planning, after partitioning comes floor planning. Floor planning is the relative ordering of the different sub blocks. Then with some additional information and refinements, we get a more accurate picture, which is placement. And after placement, we carry out routing when the geometry becomes finalized. Well, in this flow I am not showing compaction, but compaction is implied. So, from the output of routing you can move on to the fabrication phase. So, I am not going into detail of this because we are not that much interested in the fabrication phase. So, after the routing phase, the layout is ready. So, there are some feedback paths also, like there is a step called pre-layout simulation. This is typically used to verify the higher level design. So, either from the output of the partitioning phase or from the output of the synthesis phase, you go back, do a simulation, and from there you may refine your design and again come back. Similarly, there is a step called post layout simulation. So, post layout simulation, typically this is done after a process called circuit extraction is carried out. So, what this circuit extraction step does, it takes the output of the routing phase, which is a layout, and from the layout it tries to extract back the circuit, and after extracting back the circuit it gives it to a simulator. Now, this simulator is more accurate. So, here the basic components are transistors, resistors, capacitors, that way. So, this can carry out simulation in a much more accurate way, and if it does not satisfy the the timing or the power specification, you may go back to floor planning and make some changes there, or you may even go back to placement and routing phase also, but I am showing it going back to one phase only. And in this overall phase, I also mentioned at the beginning, so up to partitioning you can say this broadly is called the front end CAD design tools, and there is a small overlap here, and the remaining part these are called the back end design tools. Now, what I have had mentioned, in order to understand the back end steps, some of them at least, it is important to have some idea regarding the target what you want to fabricate. There are some VLSI design styles that people follow, and depending on the style the algorithm may be working differently. So, we first look at the typical VLSI design styles which are used in practice. Broadly speaking, there are three different styles. One is using programmable devices, other is called semi-custom design, and the third one is called full custom design. Now, in terms of the complexity goes up in this direction. Full custom design means you are trying to design almost everything from scratch. Semi-custom design means you are trying to use or utilize some kind of standard cells which are available in the library, and you pick and select them and put on the floor of silicon and interconnect them. But in contrast, programmable logic devices are something which are already prefabricated and are available in the market. So, you get them and you try to map your design onto them. They are programmable in that sense, that means you can configure them in a way so that any designs can be mapped onto them. So, there are user programmable or user configurable devices like PLDs or FPGAs. There is also something called gate arrays which also can be configured, but you will have to go back to the manufacturer for that, users cannot do that, right. So, this is roughly the spectrum, the different kinds of design styles people use. You will see that depending on which style you use, the requirement of placement and routing, everything will change. Huh? PLD and FPGA, these are some devices which you can buy from the market, and using a programmer in your laboratory you can map a design onto it. So, it can be done by yourself, but in contrast for gate array you will have to go back to the chip manufacturer, tell them your specification, they will give you back the finished product, but that is not as complex as compared to standard cell or full custom designs. This will see means what are the differences. So, we start with the programmable devices for which these FPGAs are the most common today. Okay, so, we particularly talk about FPGA, and means one particular family of FPGA we will have a very brief look at. Now, as the name implies, field programmable gate array means that you can program it on field, that means your lab. So, this is the biggest advantage of FPGAs, that it supports user or field programmability. Roughly speaking, an FPGA consists of an array of logic cells. Now, these cells can be quite complex, it may not be as simple as a gate, it can be a fairly complex functional block, it can also contain flip flops. They are typically connected through routing channels, and the functionality of these logic cells and these routing channels both are programmable. Since you can program both, any netlist you have, you can map it onto them. Talking about logic cells, now inside an FPGA chip there are broadly two kinds of cells. There are special input output cells which typically reside on the periphery of the chip. There are special logic cells on the periphery which typically control the input output points, the testability, clock, etc. These kind of things are there. and of course, there are the regular logic cells which are all inside. Logic cells can be implemented using many ways, but most of the modern FPGAs today, they use some sort of a lookup table based designs. We will see what this means, and there can also be a limited number of flip flops inside the cells, and these cells can be interconnected. Well, like here again, two different technologies are used. One uses switches which are controlled by data stored in static RAMs. Now, externally if you load the RAMs, the interconnection can change. So, this kind of a solution can be reused. It is not a one time use. You can again change the content of the RAM, interconnection changes. But in contrast, there are some chips which can be programmed only once. It is based on something called anti-fuse technology. See, normally what is a fuse? Whenever you pass a high current, there is a disconnection, but anti-fuse is different. Normally there is a disconnection. If you try to pass, or means if you apply a high potential difference, that means a conducting path gets established. So, Actel is a company which used anti-fuse elements in some of its FPGA families, but now again they have also started using SRAMs. Now, Xilinx is one of the popular FPGA manufacturers which uses an architecture which is based on lookup table and SRAMs, which is completely reprogrammable. You can use it over and over again. So, I am trying to give you a very brief outline. This picture is very small, you cannot possibly see it very well, but what I want to tell you is that, say this is the floor of the FPGA, there are some IO cells on the periphery, and inside there is an array of the logic cells. The logic cells have a particular architecture. We will be talking about this architecture. So, this architecture is capable of realizing some logic functions. The IO cells also has some programmability. You can say that whether it will be an input port, output port, whether it will be strobed by a clock, etc. And interconnection among this line is again through some programmable interconnect. This also we will see very shortly. So, this is how the architecture looks like. There are some IO cells, there are some logic cells which are called configurable logic blocks, and there are some programmable interconnects through which you can interconnect them. Now, the configurable logic blocks constitute the heart of the system. This shows a very rough block diagram of the CLBs. Now, each configurable logic block looks like this. There are some combination logic modules, there are some multiplexers for switching, and there are two flip flops. Now, each of the CLBs have a functionality like this. And you can see that there are two blocks like logic blocks like this with 4 inputs and 1 output. In fact, each CLB can realize 2 4 variable functions, any 4 variable functions, and it can also realize some of the 5 variable functions, not all. Now, the way they realize the 4 variable functions is very simple. I will tell you how. They do it using a technology called lookup tables, but essentially they implement it by using a small RAM array. See, you try to understand it like this. Suppose you have a combination circuit with 4 inputs and 1 output. Now, if you construct the truth table of this circuit, then the output column, what will be the output column? Output column will consist of 16 ones. Now, if you can store the output column in a RAM, then if you can have an architecture like this, like say you have a 16 by 1 RAM and you have a 4 to 16 address decoder. Okay. So, the inputs are fed here, this decoder will select the memory location and this is your output. So, in this way you can realize any combinational function. Now, of course, this decoder in this RAM has to be fast in order to have a reasonable performance. In fact, in FPGAs the RAMs are also designed using semiconductor technology which is fast, not using the conventional memory technology using say capacitive elements for storage. Okay. So, the CLBs can implement 4 input functions, in fact 2 of them I have said that there are 2 such blocks, and in some applications you also need some memories. So, the CLBs can also be used to implement memories. So, each of them can have 2 such 16-bit memories, right. And inside the CLB there are also 2 flip-flops using which you can also realize some, you can say, some sequential logic. There is some combinational part, there are also some flip-flops in the output of it. You can basically partition and design in a suitable way, so that you can just have some sequential logic also. And they are also fully programmable, you can have it leading edge or falling edge triggered, you can have it in the latch mode also, level triggered. Set reset can be synchronous with the clock or it can be asynchronous also. So, it has complete flexibility, you can have anything you want. I am just showing this slide. This is the diagram of the IO cells. IO cells, as you can see, are also quite complex, consist of a number of multiplexers, drivers, flip flops. So, it depends whether you want them buffered, bidirectional, clocked, what kind of interface you require. Depending on that, you have a general purpose interface block which again can be programmed to have the required or desired functionality. So, I am not going into detail of this. This FPGA routing is interesting. See, on the floor of the chip I told you that the combinational logic blocks CLBs, they are organized as an array. Now, in between the array elements there are some switch matrices. There are some fixed number of wires which are running between the switch matrices and also between the CLBs like this. Now, a CLB has interconnecting lines on this side as well as on this side. In fact, it has lines on all 4 sides. So, you can connect a signal line of a CLB to one of these lines out here. This is programmed, this can be programmed also, or you can program the switch matrix also, so that, say for example, this line can be interconnected to this output line or can be interconnected to this output line as your need arises. So, you can program this switch to specify which input has to be connected to which output. So, this switch matrix is also based on a static RAM kind of a technology, where inside there is a memory. So, you basically fill up that memory with some bit pattern. Depending on that bit pattern, the configuration of the interconnections will be fixed up. So, as you can understand that they are fairly complex things, but they are done in that way. Okay. So, if your target is FPGA, you see, if your target is FPGA, then many of these steps in the design process are not needed. Floor planning, placement are needed in the sense that which portion of your circuit will be mapped to the CLBs, individual CLB. You will have to partition the net list so that each partition can be mapped into a CLB. Routing is needed, though it is programmable. You will have to place the sub blocks into the CLB such that the routing resources which are available, they are sufficient to complete the interconnection. Because in FPGAs what happens quite frequently is that you have a design, you map it and find out the router is unable to complete the routing. Then you will have to reassign the placement and do something else, so that you will have to again go back and redo. So, FPGA design flow Of course, the first thing is design entry. You can do it either in schematic or in some description language. In case of implementation, I told you placement and routing are required. It is not that they are not required, they are required, because the CAD tool will have to know that which part of the netlist it will be mapping to which CLB, and the neighboring netlist should be mapped into neighboring CLBs, otherwise the interconnecting lines will be very long, delay will also be more. Bitstream generation is required in terms of the programmability. Whatever placement and routing you do, ultimately in a programmable FPGA, it will boil down to the bit patterns that will be required for the corresponding programming. So, ultimately you will have to generate a long bit stream which will be downloaded onto the chip and which will be programming it according to your need. Okay. And there are some tools using which you can analyze timing, see the layout, how the layout looks like, you can simulate, and finally after the bit stream is generated, you can download it directly onto the Xilinx hardware devices. Xilinx supported unlimited number of reconfigurations because they are based on static RAMs.
So then this high level synthesis and other things still need to be done, sir?
High level synthesis need to be done, everything has to be done, synthesis has to be done, partitioning has to be done, but the target of partition is different. They are not based on a technology library as such, they are based on what kind of functionality the FPGA CLBs will support, right. Fine. So, the next level up in the, if you can say, complexity is something called gate arrays. See, FPGA provides complete you can say flexibility to the user, in the case that you can just buy an FPGA chip, you have a development system, you straight away download the bit pattern, you get a working chip ready. But in order, but in doing that, if you look into the architecture of the chip, there are a lot of redundant things which you had to put it, switches, lots of memories all around. Now, means in a practical design, otherwise you would not have used like that. So, in terms of performance wise, your FPGA performance may be poor. Of course, today the FPGA chips which are available, they work with a reasonable degree of performance, but still the frequencies are of the order of 25 to 50 megahertz or so, not more than that. But one step up the ladder in terms of performance, also complexity, is something called gate array. It is not field programmable, simply gate array. So, let us try to understand what this is. Gate array comes after FPGA in terms of the speed of prototyping. Gate array is also fast, but in FPGA it can be hours, in gate array it can be weeks, right. The difference is that design implementation of an FPGA, it is done using user programming through some proper CAD tool and development system, but in a gate array you have to go back to the manufacturer. There is some kind of mask design and fabrication step that need to be done depending upon the user request. But in that case, what is the difference from a standard ASIC design and gate array design? There are differences. The cost becomes less. Gate array implementation requires two steps of manufacturing. The first step is independent of your design. The second step is specific to your design. What this means is that the cost of the first phase can be distributed amongst a number of users. Now, in an ASIC, the entire thing is your responsibility and the total cost you will have to bear. But in a gate array, the first part of the implementation, that will give you some kind of a generic gate array that can be customized for any kind of designs. The second step is that customization. Whatever you exactly require, that is done in the second step. So, the basic concept is like this. In the first phase, in the phase 1, you basically fabricate an array of transistors or gates depending on the kind of gate array you are using. Gates may be simple 2 input NAND gates, but on the surface of the chip you fabricate millions of such transistors or gates, right. So, in order to do that you have to go through all these steps of oxidation, polysilicon, diffusion, polysilicon. So, diffusion layers, polysilicon layers, oxidation layers, all these steps are already done, all these steps of fabrication are already done, and you manufacture thousands of such wafers which contains millions of transistors or gates on them. Phase 2 says you interconnect the transistors or the gates. This is again done through some fabrication process through metallization. The transistors have been fabricated, but without any metal layer. Now you are starting to put on the metal layers. Now the metal layers are depending on the user requirements. So actually for a particular design you are basically paying for phase 2, the cost of phase 1 is very small since they are manufactured on a mass scale, right. So this is the advantage of gate array, that you can have, or actually the manufacturer will provide you with a very low cost uncommitted array of transistors. Depending on your design, the manufacturer will interconnect them for you. And as I said, since we have to go back to the manufacturer fab for the metallization, so the turnaround time can be several weeks, but not more than that, and the cost will also be reasonably small. So now in terms of the performance and the utilization of the floor area, so obviously for a gate array the chip utilization will be much higher than of FPGA, because here on the chip we are not putting in any useless thing in order to achieve the programmability. Memories, multiplexers, all those things are not there. They are only useful transistors, and we are trying to utilize as many number of those transistors as we can in our design. Chip speed is also higher because all those useless things are not there. So with the present day gate array chips, you can have designs which can contain of hundreds of thousands of logic gates, and they can work with reasonable speed, say around 200 megahertz or so. These are the typical kind of performance you can achieve out of a gate array based design, right. But if you want even higher speed, even higher performance, then you will have to carry out each step of fabrication depending upon your requirement. Do not just start with an array of gates and try to interconnect them to make a flip flop, for example. So the next step up the ladder is something called standard cell based design. This is also called semi-custom. In fact, this is the most commonly used design style today. This is called semi-custom because there are some steps which are done from scratch, or done means actually quite exhaustively, but there are some steps where you simply pick up something from an existing library. You are not redesigning everything. Something you are taking as existing basic building blocks and you are trying to connect them together to form an actual design. But these chips require the entire set of mask set to be framed and fabricated. So with respect to the fab facility, you will have to pay for the entire thing. The chips will be manufactured entirely depending upon your design requirements. Basic idea is very simple. It says that you have something called a standard cell library, and the standard cell library contains all the commonly used logic cells starting from simple gates to registers, maybe small ALUs, multiplexers, everything. Now, a typical library can contain a few hundred cells. Now, in case of standard cell design, the basic, you can say, difference as compared to any other design arises out of the way this standard cell library is created. The cells which are present in the library, they have a very specific geometry or topology. They are like this. The heights of the cells are all identical. They have fixed height, but widths may vary depending upon the complexity. The reason is that it says that if you have two cells, suppose this is one cell, I am representing as a rectangle, this is a layout. There is another cell which may be longer, there is another cell which may be thinner. So, if all of them have the same height, then I can pack them together, place them side by side. So, I can have a compact layout like this, but the first cell is like this, the second cell is like this, the third cell is like this. This is possible if, since the heights are the same. Well, and since the heights are the same, you can also do a few things, like for example, the power supply lines VDD and ground. I can say that in all cells the VDD and ground lines must be located out here, so that when you put them together they will exactly touch and you have the continuous VDD and power rails, right. And the input output pins of these chips, they are available on both sides like this, and they are typically available on polysilicon layer or on a second level of metal if it is available. Fine. So, this I have just mentioned, the power and the ground rails typically run parallel to the upper and lower boundaries, so that the neighboring cells can share that bus. And if it is CMOS, there also you can follow some convention that in a standard cell the upper half will consist of the P transistors, the lower half will contain the N transistors. The reason is that when you put them all together, the top half will contain all P transistors, they can be fabricated with respect to a common well. Similarly, the N transistors can be fabricated with respect to a common well instead of isolated wells all spread. Okay. And as I said, the input and output pins are located on the upper and lower boundaries. Okay. So, a standard cell layout may look like this. I have just given a very simple example. Here these are the rows of the standard cells. So, I have shown 3 rows, 1, 2 and 3. So, as you can see in these 3 rows there are a number of cells which have been put together, and in a standard cell layout the cells are put in rows and the space between the rows are kept for interconnection or routing. So, as you can see there is some free space through which some interconnections had been carried out. This is a typical picture, and the VDD and the ground, they can be fed from 2 different sides. The VDD can be feeding the VDD lines and ground can be feeding the ground lines. So, distribution of power also becomes very regular in this kind of a design, right. So, as I said that with respect to the floor plan for a standard cell design, the total chip area will contain rows of standard cells or columns, whatever way you look at. If you rotate it, it becomes columns. Now, between the cell rows you have the so called channels, as I have shown, which are dedicated for routing. And with some modern routing technology you can also have over the cell routing, where means the place where you have the cells fabricated, the wires can also go over the cell for the routing. So, if it is on a separate metal layer, you can even take those metal layers over the cell for interconnection purposes. That saves the total area for routing, that we will see later. This is called over the cell routing. And well, since all the cells are of same height, then when placed in rows, they are put in absolutely regularly with the same height. The neighboring cells can touch each other. Well, one thing you now try to understand that your total layout will look like this, okay? Several rows with IO pins on the boundaries. Now, with respect to the back-end CAD tools, what does this placement and routing involve now? Now, placement will involve, you have a partitioned subblock or a cell of your netlist, you will have to map it to one of the rows, because now your technology library will consist of those components which are available in the standard cell library. So, you will have to map each of them into one of the rows. Naturally, the cells which are strongly connected, they must be placed closer together, right. Secondly, the problem of routing becomes very simple here. Now here you can concentrate on only one kind of routing, that is called channel routing. There is a channel with some pins on top and bottom, you will have to interconnect them through available tracks. But if you think of a very arbitrary scenario where you had a chip with some component here, some component here, some component here, with pins arbitrarily located on all sides. So, the problem of interconnecting them is much more complex, but here you have a very regular pattern. The pins are located regularly on the top and bottom boundaries of the cells, okay. But sometimes you may need to interconnect, for example, a point from here to a point from here. It is not possible to place everything on the same row if they are interconnected. So, somehow you will have to take the interconnection like this, okay. Now in order to achieve this, there are some standard so called feed through cells which are also used. Feed through cells are very simple. It is a standard cell which does not implement any useful function, just it has an interconnecting line connecting a point out here and a point out here, through which you can take a netlist from one channel to another channel, just in order to interconnect across channels. So, your placement algorithm will give you an idea to the router that how many such feed through cells you require in each track, because the placement tool will know that how many nets will be crossing across channels, right. Fine. And finally, a very brief look at full custom design. Full custom design, it is entirely up to user. There is nothing fixed or constraint which you have to follow. The standard cell design is based on cells which are pre-designed with some specific geometry. Well, in the full custom design, it is not necessarily that everything you have to design from the scratch, because today people seldom design everything from scratch. Something may be there in the library also, but they can come in all sorts of shapes and sizes. There is no restriction that they have to have the same height or anything. So in general, full custom design says that you can design everything from scratch if you want to, but in practice you use some design which you had already created earlier, you try to reuse your design. So, design reuse is an important concept in full custom design, but the designs may be existing in any arbitrary shapes and sizes, as I had mentioned. So, one area where full custom design is used quite popularly is in the design of a memory cell. See, memory cell layout is very regular, but you want to design it in such a way that it is very highly optimized. So, in that respect, this is one candidate for full custom design. And for standard logic chip design, we typically try to do a compromise between some standard cells, data path cells like ALUs, multipliers, and PLAs for implementing some means random combination logic. So, we typically mix them out together and our chip looks quite regular, but the blocks are of different sizes and shapes. So, just finally to compare between the different design styles. So, with respect to the cell size, for FPGA and gate array they are fixed, but for others they are variable. For standard cell they are fixed height, but width may vary. Cell type is programmable for FPGA, fixed for gate array, but for these they are variable. Cell placement, FPGA, gate array, they are fixed. The geometry of these cells are fixed, but you can map them differently. In standard cell you can put them in rows, full custom anywhere. Interconnects, FPGA is programmable, but for these you can do anything. Design time, FPGA is very fast, gate array is medium, full custom is the slowest. So, looking at the spectrum, you can really look at what you want. You need speed, you need fast design turnaround time. Typically when you are doing a big design, you first do a prototyping on FPGA, and if it works according to your need, then you can go for a full ASIC design, typically using standard cells. So, from our next class we will be looking at the different steps of the backend design process and we will be looking at specific algorithms, the restrictions, where they are applicable, in which design style they are applicable, and we will be continuing our discussion on backend design subsequently. Thank you.